Very good morning to you all. Today we are going to see the compensation. Here, derivative error compensation is already we have seen addition of zero. Already we have seen addition of zero. Adding a zero to the system, what will happen? That we have already seen. The effect of adding a zero to the system is nothing but adding a differentiator. Because if you add s plus z, this s is nothing but derivative of c of t. Already we have seen. So that is derivative compensation. Derivative error compensation. That is KDS. What we are getting here? E. This E is multiplied. Error is multiplied by KC means proportional. Proportional control. Proportional compensation. If you multiply E by S, it means d by dt. If you multiply but d by dt by kd, some gain k, that is called kd d by dt. That is given by this kds. S means differentiation. The error is multiplied by derivative. So there are two parallel paths. This path is for proportional. Kc times error. This path gives kd times d by dt. Therefore, the input to the system g of s is two components. One is the input to the g of s is input to the system is kc times e of t plus kc times kd times d by dt. That is d by dt. This path will give derivative of error. These two are added together. Now let us check what will happen if we add this derivative compensation. This component is called derivative compensation. Derivative compensation. Derivative compensation. This Kc multiplied by error is called proportional compensation. Already we have seen. So these two are added together, then it is given to the system. What we are giving as input to the system is Kc multiplied by error plus Kc. Why Kc? Kc is before this branch, it is there. Therefore, Kc, Kd, d by dt. These two are input to the system. What will happen to the system that we will see now? This is the original system. K upon T s square plus s plus k. It be the original system. What is the omega n of that system? K by tau. Omega n square equal to k by tau. Therefore, omega n equal to square root of k by tau. That is the original system. That is the original system. G of s equal to, that is G of s equal to k upon s tau s plus 1. What is closed loop transfer function? T of s equal to, for unity feedback system, numerator as such we have to write numerator divided by denominator plus k. That is k upon tau s square plus s plus k. That's what we got here. Tau s square plus s plus k we got. So this is the open loop transfer function. This is the open loop transfer function. In closed loop, we got this. So if you write this in natural frequency form, what you will get is k by tau upon s square plus 1 by tau s plus k by tau. Therefore, omega n equal to square root of k by tau. Since omega square equal to omega n square equal to k by tau. What is zeta? 2 zeta omega n equal to 1 by tau. Therefore, zeta equal to 1 by 2 omega n tau. That is equal to 1 by 2 omega n equal to root k by tau multiplied by tau. That is equal to 1 by 2 root k tau. That's what we got here. Zeta equal to 1 by 2 root k tau. This is the original system. Now there is no compensation. Here, no compensation. No compensation. For that, zeta equal to 1 by 2 root kt. Omega n equal to square root of k by tau. These two are we are getting when there is no compensation. Let us introduce proportional plus derivative error compensation. This line is proportional compensation. This is derivative error compensation. If you add these two, we know that block diagram reduction, this is 1, gain is 1. Therefore, this can be written as 1 plus KDS. 1 plus KDS. We can write like that. This is KC. So if you simplify further, you will get k multiplied by what you will get k multiplied by kc multiplied by 1 plus kds upon s tau s plus 1. This is what we got here. Forward path transfer function. What is the closed loop transfer function for this? Closed loop unity feedback system. That's why we can write the closed loop transfer function is closed loop transfer function T of S equal to numerator upon numerator plus denominator. Numerator plus denominator. That is equal to Kc 1 plus KDS multiplied by K upon what is numerator plus denominator. S tau s plus 1 plus Kc 1 plus KD S K. That's all. This is the closed loop transfer function. If you further classify further, if you simplify, what you will get is Kc K 1 plus KDS upon tau S square plus S plus KCK plus KCK KDS. Yes. If you group S together, what you will get? KCK 1 plus KDS upon tau S square plus 1 plus KC K KD multiplied by S plus KCK. KCK. That is equal to, if you divide this by tau, what you will get? KCK 1 plus KDS upon tau S square plus 1 plus KCK KD S plus KCK by tau. Sorry, this is divided by tau. This is also divided by tau. Now we are writing in natural frequency form. Let us assume no proportional controller. That is Kc equal to 1. No proportional controller. Only derivative controller means what you will get, the closed loop transfer function T of S becomes Kc equal to 1 if we assume K multiplied by 1 plus KD S upon by tau S square plus 1 plus Kc is 1, K KD only is there. K KD 1 plus K KD upon tau multiplied by S plus K by tau, because Kc equal to 1. From this, we understand that there is no change in omega n square. That is no change in omega n. Omega n here also the same K by tau, square root of K by tau. So derivative controller will not change the natural frequency. Derivative controller will not change the natural frequency, but it will change zeta. It will change zeta, because if you see that what is 2 zeta omega n equal to 1 plus K KD upon tau, or zeta equal to 1 plus K KD upon tau 1 by 2 omega n, that is equal to 1 plus K KD upon tau. Omega n equal to what? Square root of K by tau. Square root of K by tau. 1 by omega n means we can write tau by K. Square root of tau by K. So that is equal to 1 plus K KD upon 2 root tau K. This is zeta. What is the original zeta? Original zeta is 1 by 2 root KT. What is original without compensation? What is zeta? 1 by 2 root KT. Now what we got? Now what is zeta? Now zeta is original zeta. Original zeta equal to 1 by 2 root KT. New zeta is 1 plus KKD upon 2 square root of TD. So zeta can be modified. How much it is increased? 1 plus KKD times increased. By selecting appropriate value of KD, we can select zeta. So derivative controller can fix zeta. Derivative controller can fix zeta. Suppose your controller is, your system is oscillating because zeta equal to 0.3. Let us assume zeta equal to 0.3, original system. I want to make it 0.7. I want to make it 0.7. So what we have to do? Therefore, 1 plus KKD equal to 0.3 must be changed to 0.7, 0.3. That's the 0.3 by 0.7. 0.3 by 0.7. If we select 1 plus KKD equal to 0.7 by 0.3, then automatically the system will be modified with zeta of 0.7. So its natural frequency is not modified, but its zeta value is modified by selecting 1 plus KKD equal to 0.7 by 3. We can select zeta by using this derivative control. Already, if we change zeta, what will happen? Yes, this can be what we wrote, 1 by 2 times root KT, numerator 1 plus KKD, that is derived, we got. This also can be written like this, 1 by 2 root KT. This is original zeta. If you write this part separately, what you will get, KKD upon 2 times root KT. This way also we can write the same thing. So original zeta original. Some quantity is added to zeta, means zeta is increased. Some quantity is added to zeta, means zeta increased. So if you want to fix that zeta, as I said, 1 plus KD must be selected such a way that you want to increase from 0.3 to 0.7, means this must be the gain. 1 plus KKD must be equal to 0.7 by 0.3. That's all. Then automatically it becomes 0.7. That is the advantage. So we can modify damping zeta. We can modify zeta. That's why what is settling time? Ts equal to 4 upon zeta omega n. That we know. Zeta omega n, settling time. As zeta increases, settling time will decrease. Zeta increases, settling time. Therefore, derivative compensator will decrease settling time. In other words, it reduces oscillation. It reduces oscillation because it is increased from 0.3 to 0.7. Definitely, oscillation will reduce. As oscillation reduces, it quickly settles. Oscillation reduces, it quickly settles. That way we can see. If you want to, analytically, if you want to tell this way, settling time equal to what? 4 upon zeta omega n. As zeta increases for derivative compensation, settling time will decrease. So it improves settling time. Oscillations reduces. These are the advantages of derivative compensator. But one drawback with that, one drawback is there. One drawback. So far, two advantages we have seen. One is zeta can be increased because of that settling time. Second point is settling time can be reduced. Oscillation reduced, settling time improved. Two advantages. But one drawback is there. Here, if you see the system, what is this? What you will get at this point? Error. Suppose set point is 500 degrees centigrade. We have seen in one sum. This is 499.95. What is error? 0.05. The error is very small. Amplitude is very small. 1 point. Second thing is, all system will have noise. How noise is generated? Already we have seen. How noise is generated? Because of Ohm's law. Ohm's law says at constant temperature, V is proportional to I. V is proportional to I. Even if you apply constant voltage, current in the circuit will not be constant if temperature changes. But room temperature will not be a constant. It always vibrates about a particular temperature. Therefore, always noise is inevitable in a circuit. So noise amplitude is 0.05 volts, let us assume. Noise amplitude is 0.05. Here error also 0.05. How to distinguish between noise and error? It is not possible. That's why this this d by dt, that too d by, what is the meaning of d by dt? Rate of change of error. In other words, d by dt is slope of error signal. Slope of error signal means, suppose error is varying like this because of the slope of this is d by dt. Slope of this line is d by dt. D by dt. This is error is varying like this. Noise also varying like this. That's why it amplifies noise also. It amplifies noise also. It takes slope of noise also. That's why we cannot use derivative compensator like this in most of the time. It amplifies noise. That's why we cannot use derivative error compensator this way. Instead of using this way, we can use derivative output compensation. Because what is d by dt? D by dt can be written as d by dt of r of t minus c of t. Can I write like that? Because e of t is nothing but r of t minus c of t. Suppose I want to maintain the output always 500 means, what is the change in r? No, it is a constant. Most of the time it is constant. Most of the time it is constant. Therefore, d by dt is equal to, if r of t is constant, minus dc by dt. dc of t by dt. d by dt is nothing but dc by dt minus dc by dt. Am I correct or not? So instead of differentiating error signal, because its amplitude is very small, already we have seen final value of temperature is 499.95. Therefore, the error amplitude is 0.05. Noise amplitude also 0.05. So it cannot distinguish between the two. It amplifies both noise as well as error. Because d by dt is slope of that error signal. If error signal is noise is varying like this, see the slope. Slope is, if you draw the slope for that, slope is this much heavy. So noise is heavily amplified in derivative compensator. So what we can do is, instead of amplifying error, we can amplify C, because most of the time R of t is constant. D by dt can be written as d by dt of R of t minus C of t. Since it is constant, if we differentiate this, it becomes 0. Therefore, d by dt equal to minus dc by dt. So instead of putting the derivative compensator here, KDS, here we remove that and we put from the C of S. So that is called output derivative output compensation. Derivative output compensation. The effect is same. The effect is same. The effect is same. You see that you can find the closed loop transfer function. You can find the closed loop transfer function for this. What is the feedback path? Feedback path is 1 plus KDS. Am I correct or not? These two are parallel. So if you simplify this, finally you will get this same. What we got in the forward path, we got the same. We got the same. So 1 plus, instead of 1 by tau, we got 1 plus KD times 1 by tau. So there is no change in the zeta value, we can observe that the natural frequency is not changed, but damping ratio is increased by 1 plus kd times. So instead of using the derivative compensator in the forward path, it can be used in the feedback path. It can be used in the feedback path. Why? Because C is 500. It varies about 500. Here it is very small signal. Here error means very small signal. You cannot distinguish between error and noise. But here C is very big signal. Noise is superimposed on that. Noise is superimposed on that. So noise cannot dominate here. Noise cannot dominate here. So instead of using d by dt, here we are using dc by dt. The effect is same. The effect is same.